cute. Okay, so today we have, I sent out homework last week, and it's those pages. Go ahead and upload that to Canvas. I believe we do that this week sometime. I'm going to be, I just don't want you to get behind, so don't go too much past the deadline, but I'm not going to keep hard deadlines right now because we're all, time challenged and trying to structure our lives around all these new things. So, but I would like you to turn those in hopefully this week, upload them to Canvas, and I'll start grading those as they come in. I have not graded the group project because one of them's still not in yet. So I will start doing that actually probably today, but we'll start with that. Okay, let me go ahead and, are there any questions about what we're doing this week? No? Okay, well, let's go ahead and I'm gonna pull up, where is that? The file for today. There we, okay, no, it's on the iPad, that's right. Okay, week 4, part 1. So let me go ahead and share my screen. So the gist of this is we learned some things in just looking at spectroscopy. We could look at what the molecular weights were. We could try to figure out how many carbons we had. We could get some information, but not a lot of information. Now in IR, we got additional information specifically about functional groups and what functional groups we have. Now, what we're gonna do here is we're gonna start with our mass spec, get kind of our masses and do our rule of 13, and then look to our IR to see what kind of substitutions we should be doing. So for example, if we look in the IR and we see that we have something in an amine, we'll know that we want to do a substitution for a nitrogen. Although we should have seen that in our spectrum anyway, but we'll take a look. Okay, so that being said, let me go ahead and move these over here. Looks like we're all here. No, we're missing one, but that's okay. We have the video on. Okay, so I got a whole pack of new styluses, so hopefully that'll work really well for me. Okay, so I'm going to start with our first thing that we're going to do. We're going to take our first guesses, and we're going to then support that with what we see in the IR. And then what we see in the IR, we're going to go and support what we see in the mass spec. We're going to go probably back and forth at least 3 times. Okay, so the first thing we see in our mass spec is a 114, okay? So let's get an empirical formula based on the 114. Where's that? Okay. Divided by 13, and let me get that calculator out. You will be able to use a calculator on our exams, by the way. Just make it a low-tech one and not a high-tech one. So, 114 divided by 13 is equal to 8. And let's put the 8 up there. Right there, and so 8 times 13 is equal to 104, which gives us 10 as our remainder here. So C13, H23 is our starting point, okay? So if that's our starting point, let's go ahead and see what kind of substitutions we should be doing first, okay? So let's go to the mass spec, the IR. And the first thing we notice in the IR is that, well, we have nothing above 3,000. So we're probably no alcohols, no amines, unless it's a tertiary amine, and no aromatic rings. So that's good. Looks like we have hydrocarbons here and we don't have an aldehyde. So, ooh, we have a peak here. And that is a 17, right at between 1720 and 1700. So we're suspecting that is a
ketone?
Carbonyl?
A carbonyl, possibly a ketone because it's right in the middle, right? So it's definitely a carbonyl, probably a ketone because it's right in that middle zone. Okay, so that's great. Okay, so if we have at least one ketone here, let's go ahead and go up and do a substitution for oxygen. Okay, so if we come up here and we substitute oxygen, oxygen is equal to 1 carbon and 4 hydrogens, right? Because it's 16. So that takes us down to C12, H19O. Okay. So, wait, is that right?
Should be C7.
Shouldn't it be
14 or
C8
and then
plus
H.
8 plus 18. Ah, see? That's why we write things down, because that would have been a bad mistake. So that takes us, instead of what I just wrote, that takes us to
C7,
C7.
H14.
So our second blush is C7H14O. Okay. So, so let's say, okay, so we have that. That's telling us something. And we have, all right, so I think that's consistent with, our IR is consistent with our mass spec right now, right? So let's start looking at fragments in the mass spec to see how that ketone possibly could be linked. Being that we have no other peaks in the IR, I think ketone's a strong case, and so we should start building our case for the ketone in the mass spec. So if we get our book out, and let's look at our major fragment here of 71. That's our base peak right there. Since our parent ion peak is 114 and our parent and our base peak is the 71, what kind of fragment typically associates with 71? And I should have paged that. So I'm getting a C5 H17 or a C3 H7 carbonyl. So just by looking at our book here, we see a fragment that might contain a ketone. So I'm going to take that. So I'm going to change inks again so we know where our data came from. I'm going to erase that. So this 71 here could be a carbonyl with 3 carbons hanging off of it. And so that's our big 71 peak. And what's our 58 peak? That's our next peak down. That could also be a carbonyl with a, oops, that doesn't show up very well over there. A carbonyl with 2 carbons on it would be this 58 peak. And what's that 43 peak? Ooh, that 43 peak is a C3H7. Yeah. Okay. So we have our major fragment is this right here. And that has a total 1, 2, 3, 4 carbons plus a carbonyl. And we have another major fragment that's 3 carbons with no carbonyl. Okay. So we have 2 major fragments. And I'm going to take away this one right here because that one could be from either section right here. So if we have those as our 2 major fragments and we put those together, what do we get? So our first proposed structure is by adding this fragment here to that fragment there, 1, 2, 3. All right, so what's our empirical formula of this proposed structure now? We have 1, 2, 3, 4, 5, 6, 7 carbons, C7, O1, and then 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12, 13, 14 hydrogens. Okay. You see how those 2 fragments fit together and we got our empirical formula? Okay. So the fact that we have a fairly clean fragmentation pattern and a fairly clean IR also suggests we have a symmetrical molecule. So it's not a hard and fast rule, but it's a suggested rule. So Judging from everything we see here, I think that we probably have just solved that molecule. Okay, mass spec fit, fragments fit, IR fits, and there's nothing that discounts that particular structure. Okay. Any other proposed structures? If we wanted to double check it, make sure it wasn't a ring, we could actually do our hydrogen deficiency index here. And so we have 7 plus half of 14 plus 1. So we have a hydrogen deficiency of 1. If you want to do the math. So that accounts for the double bond of the carbonyl. So all the data fits. Okay. See how we went back and forth, got more information. It's really great, especially when you're looking for what to substitute. Because what to substitute, sometimes, you know, you're like, well, is it 2 nitrogens or something? The IR gives you an idea of what to substitute first. All right, any questions about problem number 1?
I have a question. Why did you erase near like the 58? Like, why did we kind of rule that one out?
We didn't rule it out. It's just that it was a fragment that looked like this, CH2, CH2. And so all it told us was that we had a carbonyl in there. No. So, so it still supports our data, but by having the 2 major fragments fit together, it actually builds the molecule.
Okay.
So this secondary peak right here still supports our theory. It does not discount our proposed structure. It just says it fragmented in a different way. And it was fragmenting here and here. And so I bet that's our peak down here, is those ethylene peaks. Okay.
Okay, thank you.
But especially in symmetrical molecules, you'll see these much stronger peaks with fragments to try. Focus on those first fragments first, and then second fragments to support your evidence. Okay? All right, welcome. We're now on page, problem number 2, right here. Okay, and so we have a fragment at 115, so that's interesting. Okay, so that gives us 2 possibilities. Having that fragment at 115 gives us 2 possibilities. We either have a nitrogen, an odd number of nitrogens, 1 plus X, an odd number of nitrogens, or we have an alcohol. Because remember, alcohols, when they ionize, will pick up an extra, will lose the hydrogen. And when they ionize, and therefore it can give us, alcohols can give us an odd number as well. Okay. So to figure out which one we want to use, we'll look at the IR, but after we calculate our first empirical formula. So we have a 115. So let's do 115 divided by 13 is equal to 8 again. So we have, let's see, C8 here. 13 times 8 is equal to minus 115 is equal to 11. So 11 plus 18 is 19H19. So that's, I think, our base peak right there. Okay, so that gives us an odd. That'll give us a number that is giving us a non-whole number for our hydrogen deficiency index. Okay, now the only time we get an odd number in our hydrogen deficiency, a non-whole number in our hydrogen deficiency index, is when we have a charged species, an ion. So that supports our ion species as well. Okay, so let's go to the next piece of information we have. Okay, so now that we have our empirical formula, we think we're going to have to substitute it because we have either a nitrogen or an oxygen with a hydroxyl ion. Let's look at the IR. What's the first thing we see in the IR?
The broad peak of hydroxide.
Big hydroxyl peak right here. Exactly. Okay. So we have a big OH peak. We have no ketones, no carbon-carbon double bonds, no carbon-carbon triple bonds, and we don't have any sp3 hybridized carbons with hydrogens. So we have a completely aliphatic alcohol of some sort, okay? So let's go ahead and go up and do our substitution for this alcohol. And so our O is again 16, so that's a CH4 is what we're going to substitute. So that's going to bring our new empirical formula to C7H4 is 15. And we're going to assume that's a charged species there, which means we might have to add a hydrogen to it eventually. Okay. So now now let's look at our major fragments here. Okay. So if we look at our major fragments, move over to here. All right. So this is kind of a minor fragment, but this is a major fragment. 87. What is 87? Looking at our table here, we have a couple carboxylic, a C3H7O CO2. That's interesting. C7, C3H7 CO2. That's a possible peak. Okay, so so that means it could have 2 oxygens in it and still have a hydroxyl on somewhere. But okay, let's look at our next peak. What's our 69 peak? That is a C5H9 is one of them. So this one over here is C5H9 is a major peak. That's 69. CF3, probably it's not a CF3. And then some conjugated ketones here, or unconjugated ketones. So let's call that formula one of our major fragments. And what's the one under here? I just drew it. 59, okay. So our 59, what could 59 be? Ooh, it's a CH3CH3COH. Oh, so we have a fragment of an alcohol on this one at least. This one right here can be a OH with a fragment there. What else could it be? 59 is also C2O CH2CH2. So a C3H7O is that fragment as well. And any other useful fragments here? Ooh, there's a CH3CH2CH2O. And then there's another. So there's several different 2 and 3 carbon chains with oxygens on them. Okay. So let's see what the last ones are. We have 41, which is a familiar peak. It's a CH3CH5. We have the 43, which is a C3H7, C3H7, and this one is a fragment with a C2O on it. Okay. So we have several fragments that have oxygen on them as alcohols. Okay. So we have strong evidence in the IR that we have an alcohol. We have strong evidence in the fragmentation pattern we have an alcohol. And it might be branched. Okay. Why do I say it might be branched? Or it might not be a straight chain alcohol?
Straight chain should have a lot of fragment in the reference of 14. So
Exactly.
it's not showing here.
Right. You're not just seeing loss of water, clip, 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 clip off CH2, CH2, CH2. We do not see that. So that tells us two things, one of two things. It either is the alcohol is not at the end, or you have a branched alcohol of some sort. Okay. So let's see, and let's see, the loss of this right here, I think is 15, 16, 17. Yeah. So if we look at this loss right here, this this is 17, which is OH. So that tells us what our major fragment is here. This 89 is going to be telling us what our chain looks like without our alcohol on it. Okay, because that's the loss of that. So this 98 only shows us as a C7H13 or a cyclic compound. So it's a C7H13 carbon chain plus OH. All right. So, and the only thing we know is that it doesn't have the OH on the end. So let's see. So we should be able to figure it out from its major fragment, right? So if our major fragments here are a C5H9 and something that has the 3 other carbons and an OH on it, where do things fragment when you have a heteroatom? They fragment adjacent to the heteroatom if they're on there, right? So if we have this as our straight chain, that means we're going to have, based on this peak right here, we're going to have 1, 2, 3, 4, 1, 2, 3, one of those chains. And then based on this fragment, we're going to have 1, 2, 3 carbons, 3 carbons with an alcohol on it somewhere. And so if we join those 2 fragments together, hold on, I think I have an extra carbon on there. Let's join that. So we have 3 carbons here, and then 1, 2, 3, 4, 1, 2, 3, 4, 5. Okay, do we have the right number of carbons? So all we've done is add this fragment to this fragment. Okay. Remember, this is the C5 one. This is just our empirical formula. So we've added our C5 fragment to our C3OH fragment to give us this. Now, is that the right empirical formula? I don't know. 1, 2, 3, 4, 5, 6, 7, 8. Well, we have 1 extra carbon. 1, 2, 3, 5. Oh, okay. There we go. So we can get fragmentation here and here to give us the C5. We can get fragmentation here to give us the C3OH. And we can get fragmentation here to give us our 98. Okay, questions? So it could be this. It's definitely some kind of branch. It's definitely something that can break off 5 carbons in a row. So this is about as much information as we can get from these 2 things. If we had an NMR, we could verify that this is the exact structure. But, so somebody has a question, or is that feedback on that? Okay, good. All right. So what we have here is we've put our major fragments together, and we've put we know that it's branched or substituted somewhere in the middle. And we know from our hydrogen deficiency index that if we put a proton on there, we have a saturated hydrocarbon. So I added a proton to this right here, which gives us 7 plus 8 plus 1. 7 minus 8 plus 1 is equal to 0. So our hydrogen deficiency is 0. Okay, questions? This is why we need a lot of scratch paper when we do this on the exam. Write down your supposition, and then when something is proven wrong by something else, write that out and keep circling the ones that still support what you're doing. Okay? All right, any questions about this one? You want to move on to number 3? Okay. It takes practice looking for things. It takes practice on thinking about what is a good thing and what's a bad thing. Okay, let's see what we got here. Okay, let's go to number 3. All right, so here, this is number 3. And we have a very large mass difference between what's happening and what we see. Okay, so what's the first thing that screams out at us in the mass spec? There's two big things that should scream at us in the mass spec right now.
The benzyl and the M+2.
This or this? The 170 and 172 peak? Let me see if I can get rid of that. There we go. So, because we see those two peaks at 170 and 172, there's an M and an M+2, and they're almost equal height. That's telling us one thing, which is, oh.
Bromine.
Bromine.
All right, yeah, sorry, I didn't have the chat open. Now I have the chat open, so, okay. Yeah, bromine and the 91 peaks, our next big peak right here. So this is telling us bromine, and it's telling us we have 1, okay? Now the mass of bromine is 79 and 81. So when we start calculating our empirical formula, we want to remove that first and then figure out what we have. Then the next thing we have is this 91. And what's that 91 peak?
Tryptophan?
Tryptophan ion, right. So we probably have somewhere in here. So I'm going to put things we think we have here as 1 bromine, and we have some benzene ring with a methyl group, or at least a carbon here.
Benzyl.
So that's the okay. So if we remove, let's see, the 170 minus 79 is equal to 91. So that's the peak we get, is 91. So that means our main fragment is 91. And if we look at our 91, it should be a C7H6, or a benzene ring with a carbon and 1 hydrogen on it. Okay, so that's probably our major fragment. So now we have bromine and that major fragment and nothing else. Okay, so now let's go look at the IR to see if that supports our theory. Okay, so if we look at the IR, I'm going to pull it up a little. We have a little bit under 3,000. We have a peak above 3,000. So that's great. That's telling us something. And we have this peak here. It's not very strong, but what is that peak? And there's a reason it's not very strong. I think this is a carbon-carbon double bond that's alternating between long and short. So it's what we see in a benzene ring. We get a very weak signal for that. And then this is obviously also a carbon bond, but it tends to be a fingerprint region that we don't want. One of the weird peaks that actually shows up very strongly, I think that's a carbon-bromine bond. Now that carbon-bromine bond is already supported in our mass spec, and it's very hard to assign things there, so I want to just maybe say it's that. So based on what we see, we lose bromine and we immediately get a tryptophan ion. So that's telling us those two fragments are just basically added together. Benzene and bromine. So it's benzyl bromide. Okay, why do I say it's on that peak here and not over here on bromine somewhere?
Because of tryptophan?
Because of the tryptophan? Yeah, and that's it's a very big fragment, and bromine, that bond is really easy to remove to give you that tryptophan ion. Okay, so there is, yeah, that's going to be probably the biggest one, because our tryptophan is a benzene C6H5 plus a carbon with a hydrogen on it. So that's highly supported by that. So I think it's this benzyl bromide. Okay. And to be sure, we can actually go with our 91 and calculate our hydrogen deficiency index and see if we have it right. So just to double check that, I'll do the math real quick in my head. 91 divided by 13 is going to equal to 7 carbons exactly. So it's 7 carbons and 7 hydrogens. That's 91. And if we look at our hydrogen deficiency index is 7 plus half of 7 plus 1. So that's 3.5, which gives us 3.5. So we must have an ion. And so that gives us a hydrogen deficiency of 4. If we can't have that half because of the ion, we add a hydrogen, and that gives us our hydrogen deficiency of 4. All right. All right, next one's gonna get harder, okay? So, but if you use the same process, go back and forth, you should be able to figure out every single time. Uh-oh. This one has an interesting pattern in it, and it also has with it a section that's blown up, okay? Now, this happens sometimes if the parent ion is really heavy or has a high boiling point. We'll see that this is kind of given an indication that it's kind of blown up. And notice we have a doublet here. We have a doublet here, and we have a doublet here, okay? So first of all, what do we think those doublets are associated with? I agree with the Zoom chat there. Okay, so I agree that these are bromine because we have that perfect doublet, doublet, doublet. Now, but what this does mean is it looks like we're losing a fragment that's not bromine. We're losing not bromine. And so that we need to start looking for what those fragment losses are. Okay, so if we go 150 to 121, 150 minus 121. Okay, why am I taking the two that are on the same side of each other? Because the isotopic ratio, we would do the 2 left ones or the 2 right ones. They should give us the same number, but that's the fragment we're losing, and that's a fragment of 29. And 29 is a pretty common fragment of the C2H5, okay? So this right here, this number 1 part here, is telling us C2H5, okay? So that's good. And the bromine's still on there. That means the next fragment breaking off has something to do with the bromine still on there. The next fragment breaking off is a 21 to 107. And, oh, that's 121 minus 107 is equal to 14. And 14 is associated with CH2. Okay, so we have a fragment of 3 come off, a fragment of 2 come off, a fragment of 1 come off, and then the bromine comes off, okay? So what would the fragment be if we lose bromine from the first one here? Let's start losing bromine, okay, from this one right here. So we have 151 minus 97 is equal to a fragment of 71, okay? So if we just lose the bromine on it, we get the fragment 71, okay? And fragment 71 is a C5H7. So this is 3 right here. 3 is C5H7. 7. Sorry, H11. Okay, so that gives us an idea of what the parent chain is, okay? Because this is just the loss of bromine, which means this should be our longest chain in our system. Should be a 5-carbon chain is our longest chain possible in our system. Okay, what's our 55? It's a the C4H7 and our 43. Is C3H7. Okay, that's fine. So we have a fragmenting chain, but it's fragmenting in a weird pattern. So it's not doing 14, 14, 14, 14, although it did do a 14. So it's probably not a bromine at the end of a chain. It's probably a bromine somewhere in the middle of the chain. Okay, let's go see what we see in the IR and see if we can get any help from the IR. And the answer is absolutely no. We have nothing here. We have only aliphatic hydrogens, and we have nothing until we get to carbon-carbon single bonds. So, and this probably is our carbon-bromine. So the IR is not helping us any. All right, so let's start proposing a structure. Okay, so we say it's a C5 chain, and 1, 2, 3, 4, 5, and then we have a bromine on there. Okay, but because it didn't go 14, 14, 14, 14, it's probably not that. So I'm going to suggest that we have our bromine somewhere either here or here. Okay, why do I suggest it either there or there? Okay. We have a little bit of evidence to suggest either one. Okay, so those are because they could be either one. So if we look at this fragment here, that could be this chain clipping off there. If we look at this fragment here, that could be this clipping off here. If we look at this fragment here, that just means we're clipping the bromine off. This fragment here would be clipping there again. This fragment here would be clipping here again. So looks like we have more fragments associated with the bromine being here than the bromine being here. But I think either one is a valid until we see the NMR on it. Okay. Do you see why I looked at where those different fragments were and see what's the most plausible structure we have available to it? I'd probably accept the 1 bromo or the 2 bromo or the 3 bromo because I think without an NMR it'd be a little hard. The only thing that's suggesting this is this one here is this little jump right here supports the bromine being on this one. So if you wouldn't put it, that's not a good place to put because there's nowhere to find it. So that's what I think it might be. All right. Question?
Something.
Yeah,
If you apply the 13 rule, the carbon number is C4H11. So is it not possible that that chain is of 4 carbon?
Let's see. The 71.
No, I'm asking about if you apply the 13 rule on the molecular peak.
Oh, on this peak?
Yes, and then add the bromine isotope, you will contain the C4H11 Br.
If you know you have bromine on it, it might be best to subtract the bromine first, and then do your, because when I subtract my bromine first, I get 71, and when I divide 71 by 13, I get 5.
Okay.
Okay, so if you know there's a halogen, or if you see in the IR you have an oxygen or a nitrogen there, you can subtract that from your system to help define the carbon count. Okay?
Okay, thank you.
But I mean, if you divide 71 by 13, I get 5.5 and like 5 hydrogens left over.
I had a question as well.
Yeah.
regarding the end kind of checklist there, just singling out different ideas, you got down to where there was more fragments, and is that a general rule of thumb, or is it general rule as to like how to decide between, if you're down to one or two, the one that's going to fragment more and match up with your mass spec is more likely the right choice?
It infers it. It is not absolute. That's why we have more than one spectroscopic method to use. But
Indeed.
you can get all the way down to saying, well, it's either on the 2 or the 3 carbon. I'm pretty sure of that. You can definitely, from this fragmentation pattern, and slightly lean, because of this one fragment, slightly lean toward the 2 bromo. However, I wouldn't bet money on it.
I understand what you're saying, but it is a path to get down to maybe 1, or at least between 1 or 2, and then another method will get you there, in other words.
Correct. Yeah. Okay. So everything that we've seen supports that one most. We have the most positive things toward it, the least negative things against it.
Understood.
It's a balance. It's not an absolute. Okay.
Thank you.
All right. So, all right. So let's go ahead and move on to this next one here. Okay. All right. So let's see. We have a parent ion peak of 100. Too bad they didn't tell us what that was, or else we could calculate our carbon count. But there we go. We have 100, and so we're looking at something like, oh, that's actually a C4H9 carbonyl CH2, if that was just a fragment by itself. C4, 4. So this is an actual, this actual fragment here. And let's go look at the IR now. We have no aromatics, no carbon-carbon double bonds, but we do have a carbonyl. So the IR is supporting. Okay, let's see what other information we have. Okay, so that's a good starting point. So if we start with this 100, and we know we have at least one oxygen substitution because of our IR, that gives us 100 divided by 13 is 7, and so 13, 7, 90, which gives us 9. So that's 7 plus 9, so 7, H16 is our starting point. But we know we have an oxygen, so we need to do H4 is equal to 1 oxygen. So that's going to be C6H12O. So that's our first starting point. Okay. Based on just our mass and the fact that carbonyl, we now have our empirical formula.
I have a question about how we're assigning the oxygen. Like in the past, when we've been able to tell that we have a bromine, we subtract that first and then we do the rule of 13. Why are we doing the rule of 13 and then substituting now?
I wanted to show you it works both ways, but that's just my habit. I'm sorry. But yeah, we could actually know that we have at least 1 oxygen here, but we could have 2 oxygens. So, but we have at least 1 oxygen, so you can do that exact same thing. So it'd be 110 minus 16, which would be 84 divided by 13, which would give us C6H. Yeah, you could do it both ways, but that's my habit. All right, so now we need to figure out whether this branched or something else, because how much more can we understand about this? Okay. So if this is our fragment that it kind of shows us is, so this is our major fragment. 1, 2, 3, 4, 5, 6. Oh, we already have 6 carbons and what do we have to support this additional fragment? Okay. Look right here, we have the loss of 15. We have the loss of 14. We have the loss of 14. And then we have this major fragment here, which is a C3H5. Okay. So if this is CH2, 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 does that support our current structure? And then 43, CO methyl group, or the C3H7. Interestingly enough, we can get both of those fragments off this same compound. So this spacing right here tells me it is a straight chain particle. It's not branched. This part here is supported by the 43 fragment as well. So let's see. If we move the carbonyl over one to make the carbonyl on here, we would see a different fragmentation pattern. We would see a larger fragment. We'd see a fragment at 53, which would be, no, the C4 peak would be there. Okay. Yeah, it would be a 57. We have it, oh, we have it, yeah. So, so it's probably this, or it's going to be the carbonyl is 1 over. So, but since this actually matches a fragment in our book, this fragment in our book, I'm going to say it's probably that.
Isn't the difference between 71 and 58 going to be 13, which is CH?
Oh. Oh, you're right. And then, yeah, there's this 87, yeah, CH. So that means you're getting further and further down. It's already ionized. So you've already clipped 1 off, 2 off, 3 off, and now this last one's coming in.
It could be possible that 58 is because of McLafferty rearrangement.
Let's see. Oh, because you can rearrange your, let's see, that way, that way. Trying to get that property hydrogen here to give us the fragmentation there, which would give us 1, 2, 3, which would give us a 3-carbon chain, would be this fragment here. So there is a McLafferty rearrangement fragment here if it's the long chain. So if it's the long chain, it will give that C3 fragment as well. Which is good support for the longer chain. So this fragment here was half of the McLafferty when we flipped it there. This fragment is the other half of the McLafferty. So yeah, that's a great call. I didn't see that. So that's an extra little bit of support, since it is the base peak, that we do have the straight chain and it has undergone a McLafferty ring. Okay. So yeah, I'm pretty confident it's the two with that rearrangement in there. I'm pretty confident. Good catch. All right, other questions? Okay, let's move on to number 6. Uh-oh. That IR is telling us something crazy, but let's see what we got. Okay, let's look at mass spec. The 4340 or the 7374 made me start worrying there was an isotope effect there, but that's only M+1, so I'm not worried about that. And nice fragment here at 45, a couple other there at 43, 44, I'm sorry, 73, 74, and 75. Okay, are those common fragments we see? 75 is CH2, CO2, H2, H5. So that's something to look at. So our first blush at these peaks right here is a CO, C2H5. So that's suggesting we have a carboxylic acid. Let's look at the IR. Right away, the IR also suggests a carboxylic acid. Notice that we have a big, broad peak, but it's shifted down from 3,300 wave numbers to 3,000 wave numbers. This would be an alcohol, and this is a hydrogen bonding carboxylic acid. So we're definitely supporting a carboxylic acid theory in our first fragment and our IR. Let's see what else we have. We have a 1760. Okay, so that's right in the carbonyl region. Okay, it's right where a carbonyl would be, but it's also where a carboxylic acid would be that hasn't been fully deprotonated. If it was fully deprotonated as a salt, it shifted down. So it's probably a protonated carboxylic acid right here. All right, so those are, what is the 56, 57 fragment? So these can be, what is it, C5, C4, H9, or C2H5 carbonyl. So this would be just the loss of an oxygen to go from this fragment here to this fragment here. And what's 45? Ooh, this is a COOH, or, well, those are alcohols, which we've already eliminated from the IR. So it looks like we have some kind of carboxylic acid. So I bet if we subtracted the mass from this, from the mass from this, it'll tell us what the rest of the chain is, because this is the carboxylic acid right here. So let's see, we'll look for the even numbered peak, because the odd numbered peak's probably the isotope peak. 45 minus 74 is equal to 29, okay? We don't have an actual 29 on our spectrum. Look, it's cut off. But what would 29 be? 29 is C2H5. So we have to have a C2H5 attached to this fragment here. So that tells us what we have. That answers our question right there. If this fragment is one of our major fragments, and this is the part that fell off, this must be our answer. Okay? So we worked our way all the way through the mass spec, telling us what our different fragments were. This primary fragment fits here, and it fits here. This fits in. I think everything fits in. I can't find anything that doesn't fit. What do you think? Okay. All right. So you're getting familiar and getting relaxed and looking for things that support what you're saying. All right, let's move on to problem number 7. Okay, now notice the format's changed slightly here. The format is going to be closer to what we see in our exams, okay? Because I have to use an out-of-date book that nobody's ever seen before for the exam. So notice that it's slightly different. The IR's on top, the math specs on the bottom, but all the information we'll need to be solving these should be here, okay? And since these are not actually idealized, these are actual spectrum of actual compounds, we might see some stuff shifting around. 75 minus 44 rule. No, it's not. It's the 45 fragment, which is the carbonyl with an OH on it, supports our IR. And so by just the fraction off, it tells us what is left of the molecule after the CO2H. Okay? All right, so let's go with this one. Okay, so we have, okay, so they already give us the empirical formula here. And if they didn't, we'd see right here and say, ketone. But it could be an aldehyde. But there's no 2700 peak here, so we're back to ketone. Well, we don't have enough oxygens to be an ester, and we have a carbonyl, so it's not an ether, and we don't have an alcohol. So we've got a ketone. All right, so now let's look what we got. So 72 and 57, the difference is, what is that, 20, no, not 25, it is 15, right? Yeah, so that's a difference of 15. And then 57 minus 43 is equal to 14. And then 43 minus 29 is equal to 14. So all our gaps are single carbons with hydrogens on them. Okay, what else do we see? 43 is a major peak. What is 43? Oh, 43 is one of those really common peaks because it fragments off ketones. This is excited, the fragment, ionized fragment here. So this is the 43 peak. Okay, so we have gaps of 15 or 14, and we have a 43 peak. So that 43 peak is strongly urging you to have a methyl ketone in your final system. Okay, so if we have a methyl ketone in our final system, that leaves us only 2 more carbons and 5 hydrogens left in our system. So that might be this. Okay, but if that's true, we should see the C2H5 peak. And if we're looking for our C2H5 peak, ooh, that's 29. That's our C2H5 peak. So it looks like you can have these fragments form there. That'll give you these 2 fragments here. If you clip this one off, it'll give you your first jump, this one off, your second jump, this one off, your third jump. And let's see, what else can we find? That's our only gaps and everything in there. So I think that it's probably that. Okay? All right, for the next one, I am only going to take answers in the chat room. So, all right. So what do we see?
Maybe ester,
Maybe an ester. Ooh, why?
because there are 2 oxygen and the carbonyl peak is high in the higher range.
Ah, great. Immediately looked at this, immediately looked at that, and thought ester. Okay? A very small mass ion peak. All right, so we have an ester. This structure here takes up 1 carbon and 2 oxygens. That leaves us 3 carbons and 8 hydrogens to deal with. Where do we go next? Ooh, we have another peak here, and we have this peak here. That's a good one. So the 29 is a C2H5. So that means that might be a fragment coming off as a C2H5. What's the 43?
It might be, no, sorry.
Could it be one side of the carbonyl, like cleaving right before the other oxygen and the carbonyl carbon?
So cleaving here and leaving, what group would have to be there then?
Methyl?
So
Methyl.
this could be
Yeah, methyl.
carbonyl. Okay. All right, yeah, that's definitely supported. So we have a fragment here that has 2 carbons and 1 oxygen on it. We have a fragment here that has 2 carbons on it. And we know we have an ester. Okay, so if we're just going to try to link those together, let's see. So we know, we think we have, let's do it in blue now, this fragment right there. And we have this fragment here, but we still have 1 oxygen left. And we know we have an ester. So maybe that. All right, let's play devil's advocate. Let's say you have 2 choices now. You have this one, and you have this choice. Which do you think it is? Okay. So one way to kind of ponder this, because these are only the 2 isomers we can have, right? Because we have an ester, and we only have this many carbons. So these are the 2 isomers we have. So let's devil's advocate on this and say, okay, how can you tell me it's not this one? What would a major fragment be on this one that we may or may not see on this one? On this one, we have our fragment here, and we have this fragment here. So we have 2 major fragments to support this one. What if it was the other one? What fragment should we see if it was? So that would give us a C3H5O1. Exactly. You would see a 53 peak as one of your major, because the 53 peak is the C2H5 carbonyl fragment. Okay. And so we would definitely see that fragment if it was that isomer. So because we don't see that fragment, we are supporting the fact that it is, let me draw this, not so wonky. We're supporting the idea that we have this fragment here because this is our major fragment, this is our major fragment. And we don't see this as a major fragment here. Therefore, we're sure we have the right isomer on this one. Okay? How are we doing on time? 12. Oh, okay, we're okay. We got 2 more. Okay, so let's look at this last one here. We only have 1 oxygen, okay? So, and where are the oxygen located here? Let's start with the IR. It's over here, so that's suggesting one thing. What is it suggesting?
Alcohol?
An OH group?
Yeah, definitely an alcohol, definitely an OH, definitely not a carboxylic acid, definitely not an amine, okay? Now, what we also see is no carbonyl. So that means that we only have 1 oxygen anyway, so we know that oxygen only is the alcohol. All right, what else does the IR spectrum tell us? I think it tells us two more things. Let's go to the IR first. Okay. Okay, what kind of CH? A C double bond C. Aromatic. Okay. Now, I want to point something out. I agree that it's aromatic. Number one, we have hydrogens above 3,000, but that could be vinylic or aromatic. But we don't see a strong carbon-carbon double bond, but we have this, what's called an overtone.
Overtone.
Exactly. We have that overtone pattern. That's suggesting we probably have a benzene ring in there somewhere. But we still have some aliphatic hydrogens. Okay. So these would be the sp3 hydrogen carbons that have hydrogens on them. These are the sp2 carbons that have hydrogens on them. Okay, now we've already peeked ahead at the mass spec, and Jennifer said 91. Yeah, that's telling us a big, big thing. So if we do our 91 fragment, CH right here. Okay, so let's figure out how much else we have. Okay, if we look at our empirical formula, right here we have C7H8. So we already have here C7H6. 1, 2, 3, 4, 5, 6. Yeah. So that's just the tropylium. Okay. So that means we have at least 2 hydrogens and an oxygen left. So we might want to probably look for a water loss. Okay. So water's 18. So that's pretty close to this gap here. Here. 79. 79. That's not a really common peak. 77 is benzene. Right? That's an unusual one. But the 91's telling us probably. So once we have this as this major fragment, the only thing we're missing is 2 hydrogens and an oxygen. Okay. So how can we tell whether the alcohol is on the benzene ring or not on the benzene ring? So is this alcohol? Now we have a choice. We have a choice of putting the alcohol here or putting the alcohol there.
There is a difference of 17 between 91 and 108.
Repeat that, please.
The difference between 91 and 108 is 17.
17. Okay. So that's suggesting OH is breaking off to give us our tropylium. Oh, okay. Oh, that makes sense. So is it on the benzene ring or is it on that? I think it's on the ring. Why do you think it's on the ring? It's off of the CH2. Okay. So it's going to be one of those two. The 97 peak is a C6H7. Okay, that's still 3 hydrogens more than would be on that. So, or it's a benzene ring plus 2 hydrogens, or it's a bromine. So, and there is a small 977 peak here, but it's definitely somehow the benzene has hydrogens associated with it as it comes off. So nothing in the IR to help us with that, is there? Let's see. What can I, oops. That was muted. It's been more than an hour. That's right. Okay. Let's see. What hint can I give? This is, so I think it's on this right here. Although this peak kind of gives a strong indication it might be nice and stable. And I think the fragment, I think having the oxygen here is going to help clip this off, making this 97 our greater fragment. But I don't know, it could be either one. But if I had to guess, I would say it's going to be CH2OH on here. I would call it the benzoic alcohol. OH is strong. Is the OH shifted me because of phenol? Yes. 108 minus 79. Ooh, what's 108 minus 79? That's a good question. 28. Ooh, excellent fragment. I think that does it right there. I think Neil's figured it out. The fragment of 108 to 79 equals OH CH2, which would be that fragment right there. I think you've got it. Yes. So I think it's this right here, and I think Neil just figured out the fragment here is the loss of OHCH2, suggesting that it would be the benzylic alcohol. The benzylic alcohol would definitely get most points. The OH might get most of the points, but the benzylic alcohol would be perfect. All right, great spot. All right, so now we're getting this. Okay, I got one more, and then we're out for the day. Okay, and I made it really, really hard, but I made it really easy. Okay, here we have, the first thing we need to look at is our molecular ion peak. Okay, now sometimes I'll leave this here and sometimes I'll take it off, but that immediate molecular ion peak being odd should suggest you have an odd number of nitrogens. Now, first time you think you have nitrogens in your system, look to the IR. Where should we see nitrogens in the IR? Zone 1, zone 2, zone 3, zone 4?
Zone 3.
We can see a carbon-nitrogen bond in zone 4.
Oh, okay.
And but where do we see the hydrogen-nitrogen bond?
Zone 1.
Way up in zone 1. Okay. And remember, in zone 1, the nitrogens tell us how many hydrogens we have on there.
Yes, there are two double peaks.
All 2 peaks there, right here. So that's one of our fragments is nitrogen that. Okay. So that right there, this peak right here tells us we have at least that. Let's look at the IR. What else do we have? We have this peak right here telling us one thing. That right there is our carbon-carbon bond. We have benzylic hydrogen, or benzene aromatic hydrogens plus aliphatic hydrogens. So now we have probably some kind of benzene, some kind of aliphatic chain, and some kind of amine. Okay, let's figure out. Okay, now let's go look at our mass spec. What do we see?
The tryptophan peak for the aromatic hydrogens.
Right, the tryptophan peak. So we definitely have a we have that as a fragment here. Boy, I bet we could estimate this to be 79, just below 80, right here. So loss of this to this is 91 to 107. So 107 minus 91 is equal to 16. Okay, nitrogen is 50 and a hydrogen is 1. So that's the loss of NH or CH2. So that could be either of these in that loss. The loss here is 107 minus 70. 107 minus 79 is equal to 28. Our 28th fragment is CHN2. So that's a possible fragment of 28. C2H4, nitrogen, N2. We don't have any oxygen, so it can't be carbon monoxide. So that's a possible fragment there. We have nothing of big significance. Well, maybe this one right here. This is 30. That's probably this fragment here. All right. So that's the information we can gather from our mass spec. That's the information we gather from our IR. So what's our answer? So we have NH2. We have CH something. Let's see. 1, 2, 3, 4, 5, 6, 7. And a hydrogen. Again, why do we think that this right here is attached to the nitrogen? That same thing, that fragment coming off. Notice the tryptophan's not the biggest peak there. If this was a straight chain hydrocarbon coming off here, your tryptophan would be the biggest peak. Those heteroatoms here favor a clipping at the alpha carbon. Remember, oxygen and nitrogen both favor a clipping at the alpha carbon to give you a charged fragment. So we'll see that as a major fragment as opposed to a straight chain hydrocarbon, which will clip off here, giving you the benzylic side only as your. So the fact that in both of these last two spectrum, our tryptophan was small but there suggests we do have that CH2, but there's some kind of heteroatom on that benzylic position that gives us a greater chance to cleave that carbon off than to leave it there. Okay? So it's a nice subtlety, and that's why I did it twice, is that subtlety is that heteroatom cleavage, that heteroatom assisting cleavage at that beta position that went over from the carbon. All right? All right, how confident are we feeling about this? Good? Okay. All right, we're gonna do a group activity just like this on, wait, hold on. I think we're scheduled for group activity. Let's see, I gotta look at the schedule again. Okay, let's see. Yeah, our group activity is for the day after tomorrow. It's going to be just like this. I'm going to break you up into two teams, and you're going to talk through it and come up with the best answer. If you don't get the answer, I will come and give you a hint. And hopefully everything you'll start to see how every little piece that goes. Then after that, we'll do a quick review on the following Tuesday. And then our first exam will be Zoom proctored, okay? So I'm gonna send out instructions on Tuesday of next week on how I think the Zoom thing will be working. The idea would be you have a phone or an iPad basically to the side, and you have your book and your worksheets and the copy of the test, and then you're filling out your answers. at the end of the proctor time, what you'll do is you'll go ahead and write your final answers on one page. And, well, no, you'll give me all your notes too. Your final answer and your notes on those pages. Go ahead and upload that to Canvas, and then it'll be great. Okay. So, and so we'll have that period of time. We'll have the whole time to do it, the hour and 20 minutes, more if we need. And then the idea is you'll scan it and upload it within 30 minutes of the final of the test, and then I'll start grading. Okay. Any questions about what we're doing on Thursday or Monday? Okay, I'm going to bring up some tricky ones on our on our review, but I'm going to give you a hint on the tricky ones. And so that what to look for. Hey, look at this peak. What does this mean? Kind of thing. Because I want you to, you know, those subtle things. I mean, that subtle thing, like Neil pointed out, loss was of a water, and a carbon and an oxygen together, was the perfect little nudge we needed to suggest that it was the benzylic, the phenolic alcohol. So those are the kind of the things that we need to make sure we catch it. Okay.
A couple quick questions. So we'll have the activity on Thursday. So will that be like the previous week? We'll want to go ahead and turn in our notes for that activity. And then also Friday, we'd have the homework due. So there actually are two things to upload this week. I just wanted to clarify.
Correct. And
Okay.
upload to the track site, there should be assignment tabs in track.
Yes, sir.
Sorry, Canvas, sorry. Been working with tracks for 10 years. There should be assignment tabs already in, let me double check. I want to make sure.
It's the same way we turned in the previous assignment.
Correct.
Yes, sir.
Yeah, so let me make sure that those tabs are there. The homework's there, the activity 1 is there, and I'll assign the activity 2 to right now. And so they'll all be there. They're all ready to be uploaded to.
And the homework, it looked like you didn't have like a standard sheet for it. You just gave us the problem sets. I had put it down on a piece of notebook paper, but that's sufficient to turn in, right? We just go ahead and write it down from the.
Write it down,
the,
scan it, and get it in me.
You got it.
I'm pretty flexible as long as I can read it, and if it's on the digital computer, pull it up and look for ink over ink, and I can tell, you know, what you were thinking. So it's actually kind of easier to do it that way.
Thank you.
All right, activity number 2 is up there. All right, well, thank you very much. You hang out if you have some questions. If not, go ahead and head on out to your next thing.
I have a question about my textbook being the older version, the 5th edition. I looked at the table for Mass Spec, and I'm noticing there are some differences in what is shown on here versus the 8th edition, which I have a PDF of.
Okay.
And so I wondered, would it be preferable if I were to annotate and kind of try to make them cohesive in my physical textbook, or would it be better for me to maybe print out the pages that are the Appendix B for the Mass Spec section from my PDF textbook?
I think it would be easiest to go ahead and print up the newest version of it and stick them into your book. And when you show me your book, you'll say, yeah, these are my annotated. This is, you know, because I'm actually working out of the 7th edition myself. So I had to go and look online to make sure that the homework sets were the same, and they weren't. So I had to go adjust that. And is that the, I can't tell if that's this, here, let me stop sharing and I can roll that one. That should be, does it have a, that looks like 8. Yeah, that looks like the 8th edition. That's the newest one. Yeah, that's the good one. But I mean, again, I'm working with the 7th here. I actually have a 5th as well. It has the blue clothy cover on it. I like that one. But yeah, go ahead and print up those 2 pages, because they've only added about maybe 10 ions, but we might use them. So That would be acceptable.
Okay, thank you.
I actually had a question along that line. I had been referencing Appendix B. I just want to make sure that is the one we're using for some of these, because some of the ions weren't matching up completely like with what you were saying. And I think it was just because of the count, you know, it's one way in the book or shows a carbonyl and you were just kind of adding it into the count.
So table B is all about the fragments you see.
Right.
Table C is all about the difference in the fragments.
There we go. There's my, okay. Thank you.
And usually it's plus or minus a hydrogen because of the ionization.
I was wondering about that. Okay.
Differences between a peak and a peak. Table C is what you're looking for.
Yeah.
Looking at peaks, table B is what you're looking for.
I think it was the jumping back and forth that was confusing me a little bit. I was looking at him like, I think he means that, but I'm looking at this. So anyway, thank you. It's clear now.
You know, one labeled common lost fragments, and the other is actually common fragments found. It's really, you should say found fragments, and then these are lost fragments. So this is by difference. C is B is actual measuring.
Right. Gotcha. Understood.
Remind me to draw that to everybody's attention when we start the activity on Thursday. Okay. Because yeah, that I was doing that empirically. I didn't realize I hadn't told you that, so that's important.
No problem. I may have missed that. I was just clarifying, and I was even looking at the page anyway. The jumping around kind of was confusing, but it makes total sense. No problem.
Well, I mean, you know, think of it as, you know, I need more proof. What proof do I have? 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 You know, and then so you're going to kind of back down until you have only a couple to make. So that's the key. That's the whole purpose of this. Is you can start way over here. Just by following the evidence, you'll come down to one or two possible things. Okay. All right. Well, thank you all, and I will go ahead and stop recording. Actually.